Right. So today I'll be kind of reporting on a very old paper by Balasubramanian. Um, that's written in 1996, but I think the archive version is a bit newer than that. So the title is Statistical Inference, Occam's Razor, Statistical Mechanics on the Space of Probability Distributions. That's a lot. So it's very cross-disciplinary, but I think a lot of that, a lot of things in here are things that we are familiar with, and I'm here to sort of report the paper and make connections to things that we are already familiar with. And also to point out sort of the germ of various ideas in SLT that is kind of already contained in this paper. Right, so the topics covered is include the following list. So it's mainly about model selection in Bayesian learning. It's making connection of that to statistical physics. And it include, so the Occam's razor part is kind of a geometric formulation of the principle of parsimony of Occam's razor. Right, and we'll discuss a bit about phase transition. In this that is discussed in this paper. Right. There's a note though that I need to state up front, which is this is a regular model setting. Right. That's a very big departure from our sort of the main focus of this seminar. The title of the paper is a bit of a giveaway already. So it says that it is doing the study, the inference and describing selection criteria on the space of probability distributions. And as we go along, we will observe that what he means is that we don't really care about how it is parameterized. We only care about the set of distributions we are using to learn a particular, to learn a data generating distribution. Right. Another note is that I will be using the notation in the paper, but when I discuss if there are correspondence to SLT, I will use SLT notation and convention. Okay, so a word on the sort of most popular and prevalent Bayesian selection method. So some setup. So as usual, we have a set of capital N events. The paper's notation is a set of E's, little e to e capital N. So drawn IID from a true distribution that is denoted little t, which can be confusing. So the question of model selection is, given two, I'm going to call them sets for now, two sets of distributions. So I have a set A and I have a set B. Both of them are the subset of the space of distributions. I'm not going to spell that out rigorously, but it's the set of probability distribution that is supported in the same sample space as the true distribution. So I can call that just this. Right. So we wish to, the problem of model selection is that we wish to ask which one is better for learning T if we are given this set of events. And we are using, by learning, we mean we are using Bayesian learning. So meaning to predict the probability of a new event, we are going to take the posterior weighted average over distribution inside each of these AB sets and ask how close that is to the true distribution. Right. Well, the Bayesian Bayes theorem tells us that the probability of this and this set A, this set of hypotheses, given these events or given these evidence, is equal to, well, how likely do you think this set of A is before you see anything, the probability of those events occurring, and then the probability of that event given that you are assuming A is the correct set. Okay. And this quantity here, well, now we introduce the fact that we are not just talking about any sets of distribution, we are talking about models. So A and B are model, and by that I mean parameterized models, and which means that so A is the set of distribution on E parameterized by some theta for theta in some parameter that is R to the D, right? Which means that this factor here is equal to something that we know. Right, and that is known as model evidence. Okay, so if we manage to calculate every quantity in here, so if we get model evidence, and since we are working things out in sort of the theoretical sense, people might come in with different value of P of A and P of B. So those are probably subjective. So theory-wise, we don't care about those. And if we're comparing PAE versus PBE, probability of E, probability of that event is just a normalizing constant. So really, we're just comparing model evidence. Right, so this is on a high level what Bayesian model selection tells us to do. If you have two different models, pick the one with higher model evidence. Right. So the rest of the story, as we are familiar, would just be about getting a handle on this model evidence, which is usually a very daunting task. Before that, though, there is something to do, which is a choice of prior need to be made first. And that's just a perennial debate on what choice of prior need to be made. But in some sense, this paper is, as mentioned in the title, is more concerned about the set of distribution than it is about how they are parameterized. So the parameter theta is really just an index. So there is already an implicit assumption that the map from parameter to model is one-to-one, right? So it's a unique index. The parameter space is a unique index set for the space of distribution. Right. So here we want to, if you want to have a prior on this parameter space, we want it to reflect the fact that we care more about things in its image than how it is parameterized. So we want our prior to be reparametrization invariant. Another way to say this is that we are kind of embedding our parameter space into the space of distribution. Right. And two, okay, we want prior to be parameterization invariant, but even in the image, even the image in the space of distribution, we still need to choose which, before we look at data, which distribution is more likely than the other. But the most usual choice is to say we shouldn't assume anything. We should be the most parsimonious and choose something called, follow a principle called uninformative prior. So we don't assume any information before we look at data, right? And popular choice is uniform prior or maximum entropy prior. And here we are applying that principle not on the parameter space, but in the space of distribution. So basically we want distribution in A to be equal likely according to, okay. But then this is a statement about the continuum. There is a continuum amount of distribution that we're talking about. So we need to deal with that, right? Which I'm going to say that there is a huge section, which is, I think, according to other authors, an original contribution of this paper, which is to discuss if we want to apply this principle, we can arrive at something called the Jeffreys prior, and it is characterized. So the author gave an original contribution, which is justifying the use of Jeffrey priors by stating that by doing this counting, by doing okay, let me summarize that a little bit. So okay, so we have infinite number of distributions, but we can sort of discretize them by asking if we have two, so let's say two parameter data 1 and data 2, representing P of data 1 and P of data 2. So we can ask, are they equal? Are they the same at a fixed resolution level? So what this means, so this is the concept of statistical resolution. So one way to think about that is if we are given a sequence of observation xi drawn from p of theta I, theta 1. So is this, so if I have n of them, is this enough to distinguish the that if I only observe the x's, can I tell that it definitively comes from P1 and not P2, right? And then I need, not only do I need, so as n goes to infinity, then if P1 and P2 are is actually different distribution, then you can almost surely tell if you have a large enough sample size. But for finite n, you can also distinguish them. You can ask whether or not they are distinguishable up to a confidence epsilon. Right. So the idea is that you pick an n, pick an epsilon, partition the partition A, the set of distribution, into things that are equal to each other. So take an equivalence class under this identification, and assert that this finite set of things have equal probability. And then you take n and epsilon, so n to infinity and epsilon to 0, and handle all the technical difficulties, and you can arrive at Jeffreys prior. So the important idea in here is if you read the paper, it uses something called Stein's lemma, and just to be careful, it is not the more famous Stein's lemma. It is another Stein's lemma called co-authored with Chernoff. So it's Chernoff-Stein's lemma if you want to look it up. Another way to get to the desired prior distribution would just be going from information geometry. So okay, erase those. So we want a prior W of theta such that if we reparameterize by a smooth change of charge, we get so W tilde is after the change of charge.
Do you mean, oh, phi is the new coordinate, so phi of theta, is that?
Yep.
Oh, yeah, okay. Yeah.
Phi is the new coordinate. The change of coordinate, not change. Yeah, so that's the determinant.
I really don't get the motivation for this.
Yeah.
So the whole Jeffreys prior thing, I know like Thomas really emphasized that Balasubramanian cares about it. Like, I get why it's theoretically nice, and it is a kind of, in a way it's a prior itself, right? It says that absent any other information, it shouldn't be that somehow, like, this is a kind of reasonable prior about what a model should be like, I guess. But in practice, like, the process of searching for the truth does not treat all parameters as equal, say in a neural network, right? It's like, so I wonder if actually this reflects a prior that's too pure, like it's too physical, like too physics oriented, too symmetry oriented, and actually not really a reasonable assumption about the process of searching for the truth in the systems that we actually care about. I don't know if you have a response to that.
Yeah, I do have a response to that, and the response is that basically I agree, and I do think this is kind of a major roadblock to understanding. So major roadblock to even see that there is a possibility of singularity. So because like once we continue with defining Jeffrey Prior, you just wipe out all possibility of singularity because Jeffrey Prior is not defined as singularities.
Right.
But I think the giveaway is really the motivation of this paper comes from very classic probability theory where things are usually analyzed first in the discrete case. So like the set A and B, the set of distributions are sometimes is usually assumed to be discrete. So it's like it's like choose any prior, and then if it is discrete or finite, then the uniform prior is easy to define. If it is infinite, well, you need some regularization. But then suddenly, if in the continuum, you suddenly need to do this discretization, and I think this is where this comes from. The focus is on the space of distribution, and they kind of don't care about degeneracy in parametrization.
Yeah, I wonder if I don't have exactly the opposite kind of orientation ideologically, which is I don't care about the prior because the prior disappears in the asymptotics as far as I'm concerned. So that makes me not a statistician, I guess, right? So I just don't care what the prior is, basically. For me, the prior only ever shows up when I try and do integrals, and it's a nuisance if it doesn't have a good form, like in Spencer's thesis or something. But I suppose if you're coming from Balasubramanian's background, it's rather the opposite, that you don't care what happens at singularities because you don't think about that. And somehow the need to choose a prior seems like this really objectionable thing, and therefore if you can choose this natural one that's always there, that seems like something you should do. Is that kind of where the ideology is?
Yeah, I think so. Except that's okay. So when I get to the thermodynamics point of view, there is a sense that the prior corresponds to density of states. Okay, not density of states density of states that people measure. So it's like I coordinatize my physical system in some way, and I go ahead and measure the degeneracy, like at a certain energy level, there is like you can have multiple different more configuration than other energy level and things like that. So in a sort of thermodynamics connection sense, the degeneracy is definitely very important, and which means in some physical system, people choose the coordinate first. So the focus becomes what is a prior on that parameter space. Yeah. Okay. I think we will touch on this point again. Okay. So let me sort of define the Jeffreys prior in a very quick and dirty way, and not very rigorous. So we know, I think everyone here is familiar enough with the KL divergence, which sort of measure how different how different sort of P theta 1 and P at theta 2 is to each other. And that kind of difference is what I described earlier. So how many n's do you need to distinguish two distribution at level epsilon, and as n and epsilon goes to infinity. Right. So this is not a metric, but we can do a Taylor expansion centered around theta 1. So that this will be 0 plus 0 plus, well, the quadratic term. So the constant order term is 0 because I'm doing sorry, let me actually define delta theta is equal to theta 1 minus theta 2. Sorry, theta 2 minus theta 1. So I'm doing the Taylor expansion near theta 1 of this expression. So we know that when theta 2 equals theta 1, it's 0 there, because the Kerr divergence is 0 when the distributions are the same. And the second the linear order term is 0 because we know that the Kerr divergence is always non-negative, which means that if you hit 0, it is definitely a local minima, and hence a critical point, hence the linear order term vanish. And therefore, the first non-zero term is the second order term. And J is the Fisher information matrix. Evaluated at theta 1. Right. So this matrix defines a Riemannian metric on the parameter space. Right. So and actually this is kind of a general property of divergences. Every time you have a divergence, you get the quadratic form. You can derive a quadratic form from it and get a Riemannian metric.
Everywhere it's non-degenerate, right?
Yes, that's the next very important point. So it doesn't work if J of theta is singular. So it doesn't work in neighborhoods where theta is singular, right? So okay. Okay, so using this, we define our reparametrization using the properties of Riemannian metric. We define our reparametrization invariant prior to be the Jeffrey prior, which is defined by the square root of determinant of this metric, but obviously normalized so that it is actually a density. Okay, even just looking at the form of this prior, we know that this prior is not supported whenever the Fisher information metric is singular, meaning the determinant is 0. So it immediately wipes out at any place in the parameter space where things are singular, right? And second thing to notice is that the denominator, the normalization constant, might not exist if the integral is not convergent. But if we assume that our parameter space is compact, which is a very common assumption, and we will assume that throughout, then this is not an issue. Okay. Any question before I move on?
Why is this prior like the canonical choice?
So it's canonical according to some definition of canonical. It is the prior that satisfied. It is a uniform prior on the space of probability distribution. So you have a model, and you look at the set of all distribution the model parameterized, and you say that I want every distribution in that set to be as likely as any other, and put in some smoothness condition, you get Jeffrey's prior. Does that answer your question? Yeah.
Yeah. So if the Fisher information matrix indicates that changing the parameter a little will change the model a lot, so somehow you're in a region where few parameters describe many models, then it will put more mass there. And if you're in a region where big changes in the parameter have relatively small changes in the model, so that many parameters cover only a few models, and then it will put relatively less mass in order to achieve what Edmund was saying, if that helps.
Yeah.
Great, thank you.
The extension of that is that if there's a continuum of parameters that all give the same model, then that's going to be a singularity of the Fisher information matrix. So that's going to have zero mass or undefined or something.
Yeah, I think undefined is the better one. Yeah. Okay, so so the next order of business is to list a bunch of connection of Bayesian learning with statistical physics, and then sort of start doing mathematics as if this is physics. That can be a good or bad thing. Depends on who you ask. Right. I'm going to take this from a different paper by Lamont and Wiggins, 2019. Well, that paper is kind of an sort of extension of Balasubramanian ideas and flesh out a few more things. So I think this is still counts as the same body of work. So we start with observing that the posterior distribution is proportional to the prior multiplied by some exponential weight. Okay, going to write it in a funny way, which is probably not funny for everyone here because this is a familiar thing. Okay, so what we have here is that we have the log likelihood here, and this is average negative log likelihood, which we know eventually converge to a function of theta. Right. That's the prior. Okay. So it's kind of the connection to statistical physics should sort of be gleaned from just this equation. So let me draw a table. Hopefully I have enough space. Yep. Okay, so there's a function, namely this function here, which given a theta, you compute some you compute a number that improves if the theta is closer to the true model, right? And the analogy that is that's in statistical physics, we have energy or Hamiltonian h of theta, and going across to Bayesian learning world, we get the log, well, the negative log likelihood, which is this function here. Okay, and that also means that we are thinking of the parameters as state variables. It's also denoted as theta. Okay, in statistical physics, we have temperature, T, and the inverse 1 on T, temperature, and the analogy to looking at this equation is n sample size is n is equal to 1 on T, is the inverse temperature. The prior here is like density of states. So usually the exponential weight tells you the relative probability of being in two states, theta 1 and theta 2, according to the Hamiltonian. But you need to multiply that by the degeneracy of at that state, and that's density of states. So the Boltzmann weight, so given things defined above, given a Hamiltonian at temperature T, is defined to be e to the negative, so let beta be the inverse temperature, e to the negative beta times the Hamiltonian. That's the Boltzmann weight, and then multiplied by the prior. Okay, so we have the same thing in learning land. I don't know why I repeat that, but now these things are defined in terms of statistical quantities. And then there is the partition function, which is the normalizing constant for the Boltzmann weight. So z at beta is equal to integral d theta of, running out of space, of the Boltzmann weight. And here we have Zn is equal to what we were talking about before, which is the model evidence. Okay. Usually in statistical physics, once you get your Hamiltonian, you write down your partition function. Every other quantities can and should be defined from the partition function. So it's a kind of a generating function for physical quantities that we care about. Before I talk about that, I should say that the Boltzmann distribution is just the normalized Boltzmann weight, and this corresponds to the posterior. Okay, and okay, so quantities that we might care about in statistical physics, say for example, the average energy, the ensemble average of internal energy. Well, that is defined by let me define the free energy first. Sorry. So the free energy is usually defined as negative log of the partition function. And the same thing. So free energy F sub n is equal to negative log of the partition function, or the evidence in this case. So average internal energy is given by derivative of the free energy. We have that. You can kind of see why that is the case if I use notation here. So if you sort of take the derivative dd beta into the under the integral, you get just a Hamiltonian in here, and then you are basically integrating the Boltzmann distribution against the Hamiltonian, which gives you the average energy. That's kind of the theme of how the partition function get used as a generating function. Okay, what is the average energy in statistics world? So if we look at that, so the energy should looks like dfdn. Well, I'm using capital N. Dfdn of dfdn, right? And okay, so is there a question?
I'm just trying to pass the
Pass the analogy. So
yeah.
let me introduce another
well,
quantity, and then I'll try to explain.
It's just that your formula has a beta in it, right? I mean, the partition function on the right-hand column actually has a beta in it.
Sorry, beta means n. Sorry.
Yeah,
Sorry.
and in the line above as well. If that's changed, then I understand. Yeah.
That's n. Sorry, the beta is n. Yeah.
And it's probably, this is nitpicking at this point, but somehow t is 1 on n, right? Like on the left-hand side, t is a primitive quantity, and then beta is introduced. But on the right-hand side, n is primitive. Yeah.
But primitive. What do you mean by primitive?
Well, it has a meaning. I don't have to explain it.
On the right-hand side, on
Yeah.
the statistics side.
Yeah.
Yeah, I actually think that well, I'm not settled on the interpretation, but I actually think that in this case, when we are doing this analogy, it is kind of a variable, because notice that I thought someone will call me out on this, because like in the first line, the Hamiltonian, the log likelihood has an n in there. Right?
Yeah.
Right. But really there isn't, because if I write this as this is -1 on n sum over I equal to 1 to n of p of the individual things, it's really so really I'm thinking about the large sample average version of this thing. Like I'm taking this, so it's almost like I'm thinking about another quantity called n prime, and then I'm changing my posterior distribution to ask what about n prime? What about another n prime? Kind of.
I'm not following the n prime thing.
So n prime is a kind of an independent thing. Is not
okay. Okay, you're saying that.
Not from size. Yeah.
Yeah. Okay. And this is to do with like the stochastic fluctuation or whatever. So the h somehow. I mean, you didn't actually write anywhere h is equal to that formula, right?
H equal to this.
Right. Okay.
Yeah.
So then in the formula for Zn, there's kind of a 1 on n in the h, and then it cancels with an n in front of it. But that's like not stupid, because the 1 on n that's in the Hamiltonian you kind of think of as n being sufficiently large that's really an average, and the n is like kind of like you could factor out the difference between that and the actual like true average value, and then you'd still have that n there. So that's like a real thing, and that's what you mean by the n prime, is the real thing. Is that right?
Yeah, the real independent thing that we can take the derivative and stuff like that. So even though it is discrete, we shouldn't really do the derivative. Right?
Yeah.
But so imperfect analogy, but only but works in various different regimes. Okay, right. So this internal energy actually corresponds to so if I take the discrete version, just to recall, if I take the discrete version of this, if I have fn plus 1 minus fn, that is related to the Bayesian generalization energy. So this thing is actually related to generalization error. So somehow internal energy is related to generalization error. And then there is in statistical physics, we can also talk about heat capacity. So if I inject how much heat do I need to raise the temperature by 1 degree, right? And that is that can be derived from the partition function by negative beta squared del second derivative of f. And here you can also try to look at the analogous quantity del f del square f del n square. And this is actually equal to the learning coefficient. So when n is large enough, the leading order term is actually equal to, well, it's equal to d on 2 for regular model, and in this case, but it will be equal to the RLCT in general. Okay, any question about that? If not, let's get back to our original task, which is so the model evidence now is written as, so there's a question?
Oh, sorry, I got maybe a silly question, but is the learning coefficient here like the RCT or the one used in like SGD? Or is it the same thing?
I don't think there is a learning coefficient in SGD that's called learning. I think you are talking about learning rate.
Oh, sorry, yeah, I am. No.
Yeah, so learning coefficient means the RLCT. So the rate of learning as you increase your number of sample by 1. The decrease in generalization error as you increase your sample size.
Sorry, I was away for a minute, so maybe you said, but it's actually in Balasubramanian's paper to talk about this derivative as the learning coefficient.
Is that a question or is that a statement?
That's a question, yeah.
Oh, no, it is not. So as I say, that table is based on Lamont paper, which is also based on Balasubramanian.
Okay. Yeah, that's cool. I mean, obviously, I agree with that. I just hadn't seen it being explicitly written somewhere.
Right. So using everything that we have talked about so far, the evidence now have the following expression. So there's this prior term. E to the negative n okay, so rewriting everything using the physics analogy that we have the Hamiltonian is equal to -1 on n log the average log likelihood. And using the IID assumption, we get this. By law of large number, we know that this converge in distribution, converge almost surely to the KL divergence between the true distribution and the density at theta, plus the entropy of the true distribution. Yeah, that I hope that's okay to Azad. Yeah. Okay, so we are going to do the decomposition that Dan has alluded to earlier, which is let's make this Hamiltonian. Let's isolate the part that that depends on n, and isolate the part that doesn't depend on n, or even the data set. So there's this part. Let's define that part to be this function, which is the cat the KL divergence between the truth. Yep, and define HD to be equal to well, the original Hamiltonian minus okay, notice that this has the form of a random variable minus mean of that same random variable, and which means that as you collect more and more data, so the first term is doesn't depend on E, capital E, and doesn't depend on N. The second term is something that should go to 0. So the random variable converges to its mean by the law of large number as n goes to infinity. Right. So we have, so morally speaking, the Hamiltonian energy function should be the first term. Okay, I have a question in here, which is Balasubramanian call the first term the H0 term. So we have H of theta is equal to H0 of theta plus HD of theta. Okay. This is, Balasubramanian call this term the quench Hamiltonian, and this the next term is sort of contribution from random defects. Well, so where does the randomness come from? It comes from the randomness in the samples given by E. I don't actually, so I have a very bad understanding on disordered, the statistical physics of disordered system, but my current understanding is that this term is more like the annealed Hamiltonian. So the analogy that that people usually use is that we'll study let's say we're studying a statistical physics system, say the Ising model. So the Ising model have a Hamiltonian given by the lattice and for each configuration of lattice sites we have an energy function. But we can make this a disordered system by introducing introducing defects into the lattice, and which effectively gives a random perturbation to the defect-free or crystalline model. And if we compute quantities using the full Hamiltonian and fix a particular data set, then that quantity is well, you can compute that quantity again and again for a different sets of defects. And once you compute the quantity and average over all possible defects, I think that is called the sort of the disorder average. But if you sort of ignore the mathematical validity and swap that expectation operator, so which means that let me compute the average Hamiltonian if I average over all possible samples or all possible random defects. I thought that is more like the annealed average. Dan, do you know anything about these? This is not very important.
Yeah, not enough to give a good answer immediately. I think it's probably, given our current interests, a bit of a distraction. Like, I think it doesn't matter too much. I don't think the physics is offering us much.
Yeah, except if you want to learn use replica trick or things like that in here. which I don't think we are anywhere close to doing. So
Yeah, that's a good point.
not talk about that.
Someone should give that talk soon. Maybe me.
But the upshot is that we this is the expression, but we can make the analogy to statistical physics better by talking about the anneal or quench version. I don't know. By averaging out all the defects. Okay, just to show that this thing here using SLT notation is, I guess we are used to little n, nkn w, and this is the other version using kn. So the analogy is K is our Hamiltonian, and Kn is the disordered version of that. Okay, we will go ahead and do asymptotic expansion on the expression. So Balasubramanian is using this analogy to say that, well, if n is inverse temperature, the large n limit corresponds to very, very low temperature, very, very cold temperature. So, and there is entire literature in statistical field theory about low temperature expansion. I would admit that I look at the reference given, and it's referencing an entire textbook, so I didn't actually go ahead and read what that means. But I think we have an alternative route to getting there, so I'll be presenting that instead. First, we have a bunch of assumptions, though, to even start doing this, which is we have a unique, we have a ground state. Let the ground state theta hat to be the ground state of our Hamiltonian. Well, that just translates to it being the MLE, meaning the argument over all the parameter space of our Hamiltonian, of the log likelihood, negative log likelihood. Okay, and we require that the Fisher information matrix is positive definite there. Well, otherwise, what happens if it is not positive definite? Then it is positive semi, or it's definitely positive semi-definite, which means that it is singular, which means that the prior is zero, the Jeffreys prior is zero there, which means that parameter is ruled out before we even look at so not good. So we also require that the MLE, the ground state, is in the interior of the compact. But the fact that we can define the Jeffreys prior already implies compactness. And finally, other local minima have energy bounded away from H of the minima stat by a positive constant B. So what that implies, this is a unique ground state, right? So any other minimum has higher energy by at least B, right? and finally n is large enough that the neighborhood around theta hat dominates. Well, this is a very poorly worded sentence that I wrote, but it essentially means we are talking about asymptotic regime, and n is large enough that recall that anything, any state that is away from the ground state has probability equal to exponential e to the negative n of the difference in energy, which means that anything far away from it is going to be exponentially decreasing. Okay, and from here we will just apply Laplace approximation, because the or saddle point method, or really Moore's lemma, but probably a sort of a spelled out version of Moore's lemma, or statistical field theory, which I don't know anything about, which is the actual thing that Balasubramanian used, that give us, so he introduced a new quantity is equal to negative log PAE, which means that this quantity is just a free energy, right? And is equal to n times the ground state energy plus d on 2 log n. Okay, I think the first two term is familiar to everyone. It's the order one term in this very specific case that could be of interest to us. So there is the order one term is equal to half log determinant of J, the Fisher information matrix, divided by determinant of I. Explain what that is later. Okay, so I is Hessian of H, of the Hamiltonian, right? Which is quite distinct from the Fisher information matrix for finite n. Okay, and V total is that normalizing constant for the Jeffrey prior, which means that it is the total volume of the parameter space as measured by the Jeffrey prior, which is also kind of how many total distributions there are in this model A. Okay, so the next thing is to interpret this thing with through some geometrical lens. Okay, the order n term, well, that's NH. Well, that is accuracy. Oh, I should mention that so if you're thinking of the free energy expansion in SLT, this is not quite the first term. The first term is in SLT is N KW0, right? Actually, let me just write the. No, we'll talk about. So, and W0 is actually the argument of not the perturb, not the Hamiltonian wave defect, but the annealed or quenched Hamiltonian. Right. Those two things is close to each other as n goes to infinity if our model has something called asymptotic consistency, and that just means that if you have a large enough sample set, your best guess parameter will be the best parameter, will be the parameter that is closest to the truth. And for regular model, that is guaranteed. Not for singular model though. So the first term represents accuracy. So that is just how close is the closest distribution in A to the truth. Right. So that description that I just said is closer to the SLT version, but here there is a difference between theta hat and theta star, I guess. Okay. The order log n term. Well, it's d on 2 log n. So putting on the statistical physics hat, this is degree of freedom. Or in the statistical learning hat, that's the model complexity. Well, for a regular model. Well, this d on 2 comes from, so in the analogy to statistical physics, this is this come from asymptotic equipartition theorem, and that's kind of a elementary statistical mechanics theorem that says that every degree of freedom contribute around half times the temperature. Well, there's a Boltzmann constant somewhere in there, so I'm using units where that is 1. Half T to thermal energy. Right. So remember, d on 2 is actually is in a regular case is our learning coefficient, which based on our correspondence is equal to the the leading term of the heat capacity, and the same kind of thing in statistical mechanics tells us that if every degree of freedom, so for example, gas in 3 dimension has did I forget something? I was about to say 6 degree of freedom because 3 for spatial dimension and 3 for velocity.
That's right. Times the number of particles.
Times the number of particles. So the capacity becomes 6½ nkt. I thought it's 3½ nkt. What am I missing here? I remember 3½ nkt. Where did the
yeah, I don't know off the top of my head.
Yeah. Okay. But this is I'm just saying this here to say that this is the analogy still holds in this case. And from the statistical learning side, this is related to the number of ways random fluctuation in so number of independent dimensions in which just fluctuation in the samples can cause the model to depart from the optimum, right? So yeah, so if your model is very, very complex, then sort of noise in the data can use those extra degree of freedom to overfit. Okay. So, and then I guess the less familiar term is the order 1 term. So I'm going to rewrite those 2 terms by doing some using the property of logs to rewrite them this way. Okay. So that term is so if we look at the top term, the determinant of the hashing of...
Sorry to interrupt you, Edmund. I guess I don't understand what the log n is doing. I mean, the story you were just telling was about d on 2, basically, right? But in the first line, I mean, that whole thing with the n is like a meaningful thing.
No. I was actually, the accuracy is it should be about h, just the h. So on the right-hand column, I'm only talking about the coefficients.
Yeah. Okay.
Right, because even in the order n term, if you have two states with different accuracy, so different energy, then if n is large enough, the lower energy term always dominates. Right.
Okay, so you're thinking of this in terms of model selection again, or something, right? You're comparing.
Yep.
Yeah.
Yeah. So if I'm comparing two models, one model is less accurate, and if my n is large enough, then I will always choose the more accurate model. Okay, but if n is large but not large enough for the first term to completely dominate, we look at the next term in the asymptotic expansion, and that's the complexity term. So smaller complexity, the better. And then if the n is still smaller yet, we look at the order 1 term, and the order 1 term is called Balasubramanian called this particular term the robustness. Okay, we'll explain why he called it that. So the determinant of the hashing, well, that's kind of okay. If the hashing is not degenerate, then we can and we know that we are expanding the log likelihood near its unique global minima. So the hashing is positive definite and therefore have all positive eigenvalues, and those eigenvalues correspond to the size of the axes, independent axes of an ellipsoid near theta hat. Right.
Flatness.
So the determinant. Yep. What was that?
Oh, I just said flatness.
Right. Yeah. That is right. So flatness is the larger the volume, the higher the flatness. Yeah. Exactly. So so I was about to say that the determinant of that is the volume of the ellipsoid centered at theta hat, and there's this.
Well, there's a more lowbrow way of saying it, which is that locally that means something is expanded as lambda 1 x1 squared plus ... lambda n xn squared, and the lambdas are the eigenvalues. So this is 1 over the square root of that product. So the more curved it is, the higher the lambda, the smaller this number. So the flatter it is, the smaller the lambda, the larger this number.
Yeah. The volume of ellipsoid. So the volume of ellipsoid containing good distribution. So by good distribution, so we are in the neighborhood of the MLE here. We are in the neighborhood of the ground state. So everything around it is, so I'm looking at an ellipsoid around that, and everything contained within that ellipsoid is close to the ground state. So those are good hypothesis to model the data, right? But what is the other term here? So the determinant of this of the Fisher information matrix. Well, this is another ellipsoid, but this time this is related to. By the way, this order 1 term comes from the fact that we are using a specific prior called the Jeffrey prior. So this term is related to the volume of distinguishability. So this is coming from how the Jeffrey prior is defined, which is what is the typical volume within which I can't distinguish distribution in that, right? So the ratio between these two has the meaning how many distinguishable almost true distribution they are, right? The more okay, let me draw a picture. So the picture is that's the MLE, and that's the ellipse around the MLE, and if the volume distinguishability is very small, meaning that this there's a lot of essentially different good guesses. What that means is that you don't need to specify. So if your MLE change a little bit and go here and becomes that, that is actually okay, because you are still you're still in the neighborhood of good guesses. So this is saying the more robust you are, the less sensitive you are to the precise choice of parameter. Okay, and there's a we have kind of already discussed the last term. Let me write it in the 2 pi on d on 2. So the last term, again, everything here is the smaller the better. I'm writing in a way that where it is the smaller better. So V total is just the total. So this is related to how constrained our model is. So if everything before, so if your model have the same accuracy, if two models have the same accuracy, same degree of freedom, and same robustness, then whichever model has smaller space of distribution, which that one wins. Okay. Okay. I'll quickly go through. Oh, sorry. Let me say a word about where is Occam's razor in here. So the idea is that we should be using. Now on the correct board. So the razor for model selection, call that Rn of a model. I think a sort of less philosophically inclined language for this will be information criterion in sort of modern parlance. So the razor Rn Balasubramanian claim is defined to be the quench version of the evidence. Okay, let's explain that a little bit. So right, so this is H naught theta. Okay, so this is saying if you know what the true distribution is, okay, that's a big if, but so suppose you want to study a range of phenomena, and maybe you know what class of true distribution it is, and you have various models to learn distribution in that. You want to know, you have two models, and you want to know which one you should use. Then this razor is saying, compute this Rn quantity, this razor quantity on model A, and compute this razor quantity on model B. Whichever is larger, so this is related to the evidence. So whichever has higher evidence, use that one. Okay, I want to emphasize the fact that this criterion depends on M, right? So first thing first is that this is a tall ask. This is really hard to calculate. So what you would do is to write out the asymptotic expansion of this, which is just what we have been given before. H naught of theta star plus d on 2 log n plus actually minus robustness and minus constraints. Right. So you have compute these quantities for two models and compare their leading order terms, and you can compute each of these terms. Well, the second term you don't need to compute, just count parameters, and the first term you do optimization to find out the ground state energy, and so on and so forth. Right. Obviously, this is a regular model story. I want to emphasize that this is already a more careful definition of model selection criteria than a lot of modern statistics. It acknowledges the fact that it depends on the truth, right? It is not, so colloquially people sometimes say things like complex model is bad or things like that. But here it at least knows that there is a trade-off between accuracy and complexity, and then there is even higher order term trade-off. Here I should also want to say that the SLT version of this is the very familiar. In SLT, there is actually another term, another order, which is the log n order. Which for practical value of n is probably just constant. And in the SLT, we haven't have, we can probably express the constant order term. Okay, for the next couple of minutes, I'm going to mention some generalization of that is already mentioned is Balasubramanian. Okay. I'm just going to do it colloquially, so verbally, sorry. So if you have multiple global minima, you can still fix this process. That's one assumption violated, but what it amounts to is you Laplace approximate, do the Laplace approximation at each global minima, which means that you get this asymptotic expansion at each of them, and then take the sum. Right. So the first term will still be will be a constant multiple of the first term, and the second term will be d onto another constant multiple, but the order one term will be different. Right. Recall that the order one term involve at least so now you have different global minima. And the order one term will be a proper sum of different quantities. Okay, another second step of generalization. What if the set of minima forms a smooth submanifold of your parameter space? Well, in this case, so your parameter space data, and then the set of minima looks like, say, like that. In that case, you would choose coordinate that can be partitioned into two parts, one the tangential part and one the normal part, and then do the Laplace approximation on the normal coordinates. And
wait, but it's not
integrate things out.
It's not enough for that set to be like a smooth submanifold. You'd need the Fisher information matrix to be non-degenerate as well. That's a prevailing assumption, I guess, right?
No, actually, no. So this is a local minima of the energy function, which doesn't doesn't involve the prior. So this is still a well-defined concept, right? So it is correct that the prior will be 0 there, but here we are basically saying that we...
Oh no, I'm not talking about the prior. I mean, okay, so it would be the same to say, well, what I'm saying is that the Hessian of the Hamiltonian would have to be non-degenerate.
Yes, yes. So
Oh, but that's
right.
Oh, sorry, but that's the hypothesis at the beginning that it's regular. I mean, I guess maybe it's okay, right.
The thing is, like, so basically everywhere where you are taking determinant, you are taking determinant of a matrix where there is a bunch of 0 eigenvalues. So basically, don't take a determinant of the full matrix. Take a determinant where the eigenvalues is positive, but all the other dimension integrate out separately. And integrating the tangential part out should be easy because there's only one distribution there, right? So there's a bit of redefining. So we are redefining the Jeffrey prior to be a prior on a tangential part. Sorry, on the normal part. So yeah. Okay, the first and second term would be or the n and log n term would be not too much affected, but the remaining term will be affected because well, the curvature of the Hessian of the energy function as well as the Fisher information matrix when you mod out the 0 eigenspace, those curvature are different from point to point on this submanifold. So a bit more complicated. Okay, so if your set of minima is not a submanifold but is an analytic variety with singularity, we do SLT. And I am already over time, but I guess I will stop here.
Great, thanks, Edmund.
I didn't mention phase transition, but let me just say a word on that, which is in the Balasubramanian paper, you have if you are comparing you can compare 2 minima. They have different energy, but the problem with regular model is that if you have 2 minima, you could have a different energy, so different order n term, but both of them would have the same complexity, still d on 2. So it becomes you are comparing the next order down, which is comparing their robustness and simplicity.
Yeah.
SLT just comes along and said that no, this energy entropy trade-off happens much earlier in the asymptotic expansion. It happens in the order log n term as well.
It would seem very difficult to come up with convincing examples where you have a phase transition with the robustness. No.
I mean that's the flat minima story, right? So
yeah, I guess that's true. Yeah.
Yeah.
Mm-hmm. That's right.
Right.
Any other questions for Edmund?
Question.
I don't think Edmund can do much about that, Ben.
Yeah. So the paper also talk about sort of changing true distribution, which is I think I want a takeaway from this is Balasubramanian, this paper seems to have lots of the germs of idea in SLT. He also acknowledged the difficulty with when the set of minima has singularities. The formulation here is like aside from the difference between MLE and things like that. So there is a world where and a possible Watanabe that read this paper and fixed everything, and that's the origin of SLT. Yeah.
Cool. All right. If there's no further questions, we'll leave it at that. Thanks a lot, Edmund. Next week is Ben speaking on the toy models of superposition paper, so part 2 of that.